Hello everyone. The title of this video is Solving Inequalities in One Variable Algebraically. So each example I'm going to be doing in this video is taken directly from a free online textbook at openstacks.org, and I'm in their Algebra and Trigonometry text, section 2.7, titled Linear Inequalities and Absolute Value Inequalities. And I'm working under the heading Solving Inequalities in One Variable Algebraically. The examples I'm going to be doing will either be an example from the reading or one of the try it problems from the reading or one of the exercises at the end of the section that's related to this particular objective. I would ask that when I start a new example that you pause the video and try to work it out yourself first before watching me do it, and then compare, because I really feel that you should be practicing these things on your own, instead of just watching me do it. Okay? Great. Alright, so all my examples are written out on paper, and for each of these we are asked to do the following. We're asked to first, solve the inequality, and then express the solution set in interval notation. Now, I have put out a previous video on interval notation, or hopefully you've been reading this text, and earlier in the section there's a whole section, part of the section on interval notation. So I'm assuming you know what that is. Alright, now when you're asked to solve an equation or solve an inequality, you're basically just asked, what numbers can you replace the variable with and make a true statement? Right. Now, solving these inequalities in one variable, and we're going to see that these are actually all linear inequalities. They'll involve polynomials where the highest degree term, the highest power on the variable, is the first power. Right? So all these examples are linear inequalities. So we're going to solve these in the same way we would solve a linear equation with one variable. I'm going to do what I can to, get the variable alone on one side and some number on the other, some constant. And you just have to know how to read the inequality symbol, know what it means, know what would make the statement true. Alright, so we're going to be using what are called the properties of inequality, which I'll write up over here. Alright, so first you have your addition and subtraction, which go hand in hand. I mean, subtraction is just adding the opposite, right? Subtraction really is just addition. Right? Okay, so if say A is less than B, and this can be any inequality symbol. Right, please understand this. I'm just using less than in all these properties, but please know that this can be any of the inequality symbols. Right. So is less than, is greater than, is less than or equal to, or is greater than or equal to. Right, any of those four. So if A is less than B, then A plus C will be less than B plus C. So basically, kind of like with an equation, if you add something to one side, we're going to add the same thing to the other side. Right? And the inequality symbol will not change. Right? So I'll point that out as well. Right? The symbol doesn't change when you add or subtract. Right? It doesn't change when you add or subtract the same thing to both sides. Okay? So that's a simple one. All right, then you have your multiplication slash division, right? Because remember, dividing is the same as multiplying, right? It's multiplying by the reciprocal. So the multiplication slash division property of inequality. All right, so if, again, I'll use A is less than B, but again, it can be any of the symbols. Right? If A is less than B, greater than B, less than or equal to, greater than or equal to. And then I'll break this into two cases here. One, if C is a positive number, right? If C is a positive number, then A times C or divided by C, same thing, will still be less than B times C, right? If the symbol doesn't change. All right, the symbol doesn't change when multiplying or dividing by both sides by the same positive number. All right, so if A is less than B, and we have and C is a positive number, then A times C will still be less than B times C. All right. Now, second case here, if A is less than B and C is less than 0, right? C is a negative number. Well, then A times C will be greater than B times C. Same thing for division. A divided by C would be greater than B divided by C. So you see here, when you multiply or divide both sides by a negative number, and this is for negative numbers only, positive didn't do anything to the symbol. The symbol, right, flips, you could say. The symbol flips. This is an exclamation point. Right? So it goes from being is less than to is greater than. Or, if this was is greater than, it would become is less than. But the symbol flips. Right? And this is really all you need to remember when we're solving these linear inequalities. So I can move terms from side to side with addition and subtraction, and when you add or subtract the same thing to both sides, the inequality symbol does not change. And then we can multiply. I'm trying to get the variable alone, so we'll eventually have to multiply or divide by some coefficient, some number. If that number is positive, right, and we're multiplying or dividing by the same positive number on both sides, the symbol doesn't change. But if that number is negative, right, you multiply both sides by the same negative number or divide both sides by the same negative number, the symbol will change. The symbol will flip around. Okay. All right, and I guess one final thing to point out, right, the only other time you're going to have to worry about when the symbol will flip is when you switch sides. All right, so I'll just call this last one here switching sides. because you might want to do this on occasion. So if A is less than B, right, if A is less than B, then B must be greater than A. So you see what happened here? A was on the left here, B was on the right, and it was is less than. But if I switch sides, put B on the left, A on the right, it becomes is greater than, right? All I did was really read it right to left instead of left to right, and then write it down as I read it. A is less than B, read left to right. If you read it right to left, it's B is greater than A, right? And that's what I wrote over here, so that when we read it left to right again, it's B is greater than A, right? So basically, switching sides flips the symbol as well. Right, keep that in mind. And there's also something about raising things to negative powers, but you have to pay attention to whether or not both sides represent a positive number or a negative number or whatever. But we're not going to get too detailed here, right? Just these three: adding, subtracting, multiplying, dividing, and switching sides if you wish. Okay. And one more time, the only times you're going to flip the symbol is when you multiply or divide both sides by a negative number, or if you switch sides. The symbol will flip. Every other time, the symbol will not change. Okay. So, here we have 3x minus 2 is less than 1. So you have 3x minus 2 on the left, is less than, and then 1 on the right. I eventually want to get, the variable x alone on one of these sides. For the most part, I'm going to set it up so that it's alone on the left side. Alright, just easier to read personally. So first thing I'll do is get rid of this negative 2, alright, by adding 2 to both sides. Alright, and notice I already wrote the same symbol, right? It still is less than, because adding the same number to both sides will not change the inequality. Alright, and then we have 3x now on the left is less than, 1 plus 2 is 3 on the right. And then we're going to multiply both sides by 1/3 or divide both sides by 3. Now again, I didn't change the symbol because I knew I was going to be dividing by a positive number. Right, dividing both sides by a positive number does not flip the symbol. But if that were a negative number, I would have changed it, right, flipped it around. So now on the left side I have x still is less than, right, divided by a positive number, and then 3 divided by 3 is 1. And here you go, right, here's a description of the solutions, right? So the solutions of this inequality. Now you can describe the solutions in many different ways. You probably, I talked a little bit about this in my previous video on using interval notation. We can describe the solutions in words. This is x is less than 1. So all the numbers that satisfy this are the numbers less than 1, and we're talking about the real numbers here, no imaginaries, right? So if I describe this set in words, right, it would be all real numbers less than 1. That's why I like having the variable on the left. Right. If you switched it around, it'd be 1 is greater than x, but that still tells me that x has to be some number less than 1. Okay. So there you go. There's a description of the solutions in words. Now all the numbers less than 1, like 0, -1, a half, 0.75, -1 billion, right? There are infinitely many numbers less than 1, but I can describe it in words. I can indicate the solutions on a graph, right? A number line. Here's a number line, and the variable in this inequality is x, right? And you know how a number line looks, right? You got 0 somewhere, and then positive numbers to the right, negative numbers to the left, right? You know, the numbers we're indicating here are all the numbers less than 1. That's to the left of 1. Right, like I said, 0, -1, -2, you know, 0.5, -1.5, whatever. And then 1 itself, 1 is not less than 1. 1 is equal to 1. So above 1, I'm going to put an open point. All right, and this open point indicates that, you know, 1 does not belong to the solution set. All right, and then a third way would be in something called set builder notation. So you write out the solution set. So it's a set. You got the little curly braces here. Once again, the variable is x, right? So the set of all the solutions is, you know, all the values of x, and then you put a little bar or a colon to separate the variable from the conditions on that variable. You know, it's all the values of x such that, you know, x is less than 1. This is called set builder notation. And again, it's describing the same set that all these other things are, right? All the numbers, all the real numbers less than 1. All right, and then finally, what they want us to write the solution in, write the solution set in, is interval notation. Which again, I'm assuming you know how to do this, right? That you've seen my previous video or read the book or seen other videos or other readings or whatever. Right? So the interval for I like having the picture up, you know, you always go low to high, always, you know, left to right, or low numbers to high numbers when you're writing your intervals. So this is from, you know, the left end of this picture, these numbers less than 1, there is no left end. So I'm going to put -infinity for the left end. Right, that indicates that the numbers are going to the left, you know, forever. And then going left to right, you know, this picture ends at 1. So I have -infinity, comma, 1, left end, right end. And then you cap these off with either parentheses or brackets. Right, now remember, you use parentheses when the number, you know, doesn't belong to the solution set or doesn't belong to the interval. And you use brackets, those rectangular brackets, when the number does belong to the interval. Well, again, hopefully you remember this, but, you know, infinity or -infinity, these are not numbers. Right, they're concepts. So always cap the infinities with parentheses. Right. And then we said a second ago, right, 1 is not less than 1. Right? 1 is not a solution to this inequality. So it's not included in the solution set. I'm putting a parenthesis on that as well. Right? And this is what they wanted. Right? So I'm going to put this in a box. This is actually what they asked us for. Right? Write the solution set in interval notation. Right? So -infinity up to 1, parentheses on both. Okay. And there was a lot of stuff there. Right? And again, you can test this out. Right? Always double check your work. But I leave it to you, you know. Plug in 1. You know, you'd get 1 is less than 1. That's false. That's false. So you see 1's not included. Check it out. You know, plug in any number greater than 1. Plug in 2. You'd get 4 is less than 1. That's false. You know, plug in any number greater than 1 for x and see that you get a false statement. And then, you know, plug in any number you want. Check out any number you wish. Plug it in, and, you know, any number less than 1, and you'll see it's true. You know, plug in 0. You'd have -2 is less than 1. True. Plug in -1. You get -5 is less than 1. True. Plug in a half. Right? You get -half is less than 1, which is true. Right? Again, take any number less than 1, plug it in for x, and see if it's a true statement. And then you'll also notice, like I said, plug in 1, it'll be false. Plug in any number you want greater than 1, it'll be false. Right? So just test it out. Right? But I leave it to you to do the testing. Okay? Great. Alright, so the rest of the examples are very similar to this. Very, very similar. Alright, so example 2. So once again, I'm trying to get all the variables. I personally like getting the variable to the left for these linear inequalities and constants to the right. Alright, so the first thing I'm going to do, again, I'll write these out one step at a time here. We have 4x plus 7 on the left, and then is greater than or equal to, and then 2x minus 3 on the right. And I'm going to get all the x terms on the left, I'm going to subtract 2x from both sides. Now notice, right, again, I didn't change the symbol, because adding and subtracting will not change the inequality symbol. Alright, so that would get rid of the 2x on the, get all the x's on the left. And then let's get rid of this plus 7 on the left side, move it to the right, so minus 7 as well. Right, I'm going to subtract 7 as well. And once again, adding and subtracting doesn't change the symbol. Alright, so now I simplify the sides. 4x minus 2x is 2x. And then you have is greater than or equal to. And then over here, -3 minus 7 is -10. Alright, and then once again, I kept the symbol the same because I know I'm going to be dividing by a positive number. Right. I'm going to divide by positive 2 on both sides to get x alone. And dividing by a positive number, the symbol stays the same. It does not flip. So we have x on the left side still is greater than or equal to, and then -10 divided by 2 is -5 on the right, right? And there it is, right? Now, I'm going to do the same thing for every single one of these, right? I'm going to describe the numbers that are solution. I'm going to describe the solution set in words, in a picture, in set builder notation, and in interval notation, right? The final thing will be what they actually want. Right, so the solution set here, in words, x can be any number, any real number greater than or equal to -5, right? So this is all real numbers. Greater than or equal to -5. Right. Alright, then a graph. So again, here's a number line. And the variable here is x. So I'll say this number line represents possible values of x. Here's 0, and -5 would just be to the left of 0. I'm not going to mark off every integer now. And we're talking about all the numbers, greater than -5. That'd be to the right of -5. Right, -4, -3, -2, -4.9, right, 5 million, right, forever. But or equal to, right, so -5 is included in the solution set. -5 does satisfy this. Makes it true. So notice I'm putting a closed point, a filled in dot, solid dot above -5. So there's a graph of this same set of numbers, the solution set. This is the same as saying, the solutions are all values of x such that, what I've got here, x is greater than or equal to -5. There's the same set written in set builder notation. And interval notation, the left end is at -5, and then the right end, well, there is no right end, so it's going to positive infinity. You always have parentheses on infinities, right? And we said a second ago, -5 here is a solution, so I'm putting one of those rectangular brackets, right? And don't rush these, because if you rush them, it'll look more like a parentheses than a bracket. It should be a rectangular bracket on -5 because, again, it is included as a solution. And I'll circle this, that this is what they wanted, right? They wanted the solution set in interval notation. Great. All right, and once again, I leave it to you to check some values out. Plug in any number to the left of -5. Plug in -6, -7, -5.2, -1 billion. And this inequality will be false, right? Those are not solutions. But if you plug in -5 for x, or any number greater than -5 for x, you will see that you'll get a true statement, and you should, right, if you did everything correctly. But I leave it to you to test that stuff out. Great. All right, so this next one, now this has a fraction involved, right? I know people typically don't like working with fractions, but you can always leave the fractions the way they are and move things in the typical fashion, right, as long as you know how to work with fractions. But if you don't like working with fractions in an equation or an inequality, you can clear the fractions by multiplying by the least common denominator, right, of all those fractions, the LCD, which here would obviously be 2. Right? That's the only denominator showing up in this. So first thing I'm going to do, just to get rid of the fractions, just to clear the denominators, is I'm going to multiply both sides by, positive 2. So this left side, right, -x plus 4. And because I'm multiplying both sides by positive 2, the symbol will not change, right? So it's still going to be is less than. And then doing the same thing to the right side, this half x plus 1. Right, so we're going to multiply, again, by positive 2. Positive 2. Right, and that's why the symbol did not change. If it were -2 for some reason, then I would change the symbol. I would flip it around. We'll eventually get to a case where we have to flip the symbol, I promise. All right, so over here I need to distribute 2, right, because there are multiple terms. Same thing over here. Multiple terms, multiply everything by 2. So now we have, on the left side, -2x plus 8 is less than still, and then 2 times a half is 1, right? That clears the denominator. You just have 1x, and then 2 times 1 is 2x plus 2, right? So you can always do that, always, with fractions in an equation or an inequality, multiply both sides by the LCD. Okay, so now this is kind of like example 2. Right, first thing I want to do is do some addition and subtraction to get all the terms of the variable on one side. Now again, I prefer the left side. You can put them on the right side if you want, whatever, as long as you know how to read it at the end. Alright, so I'm going to subtract x from both sides, and then also subtract 8. Right, get the constants on the right. Alright, now once again, does the symbol flip? No, because I'm only adding and subtracting. Right? Addition and subtraction does not change the symbol. That's the first thing I'm going to think about. Right? Will the symbol flip? Then I'll have negative 3x on the left, and 2 minus 8, -6 on the right. Right? And you know what? I'll rewrite this because I'm going to be flipping the symbol here in a second. Right? So there's -3, -6, and then what I'm going to be doing next, right, to get the variable alone, is dividing both sides by negative 3. Right. So one more time, I'm going to write this here, dividing by a negative number. Same thing with multiplying, right? Dividing by negative numbers, multiplying both sides by negative number, flips the symbol, changes the direction of the inequality. So on this line it was is less than. Here I'm dividing both sides by negative 3. This becomes is greater than. Right? Is greater than. And one more time, I'll even write it here. It flips, right? Because it changes direction because of this division of both sides by the same negative number. Alright, and now we have x on the left. Now it says greater than, and then negative 6 divided by negative 3 would be positive 2 on the right, right? And here you go. Right, we have what we want, the variable alone on one side, some constant on the other. And then off to the side here, I'm going to describe the solution set in those 4 ways. Right? So in words, the solutions of this inequality, the numbers I can replace x with and make a true statement, x can be any number greater than 2. Any real number, all real numbers greater than 2. But notice it's just greater than 2, not equal to 2. Right? Just greater than. So 2.1, 2.5, 2.89, 3, 4, 5, whatever. Anything bigger than 2 on the number line to the right of 2. And that'll be my next way to describe this set. Here's a number line. The variable was x again, so this represents possible values of x. Here's 0, and then 2 would be to the right of 0 somewhere. And we're just talking about the numbers greater than 2, right? To the right of 2 on the number line forever, right? Little arrow. But just greater than 2, not 2 itself. So once again, I put an open point, empty point above 2 to indicate that 2 is not part of the solution set, right? 2 is not a solution. And you can check that out, right? Plug in 2 on both sides here, and you'd get 2 is less than 2. You'd get a false statement. So 2 is not a solution. But any number greater than 2 is. Plug in 3, plug in 4, plug in 5, and you will see a true statement. I promise you. But I leave that to you to check. That set builder notation, very simple, right? It's all the values of x such that, right, bar, and then we've got it right here, right? The description, x is greater than 2. Right, so there's the same set of numbers in set builder notation. And then finally the interval notation that they wish for, again going left to right, low to high, this picture of the solution set. The left end is at 2, there is no right end, so it's going to positive infinity, and parentheses on 2, right? 2 is not a solution, and always parentheses on infinities, right? Because infinity is not a number. And I'll circle this, right? This is what they actually asked us for. And again, I leave it to you to test some values out. Plug in 2, plug in any number less than 2, and this will be false, because those aren't solutions. And plug in any number greater than 2, and it'll be true. And I leave it to you, though. All right. Next, same stuff. All right. Only this has a few more fractions in it. So here the LCD, right? Again, if you want to keep the fractions, keep the fractions, right? There's nothing wrong with that, as long as you know how to add and subtract and multiply and divide with fractions. But the denominators in this are 6, 4, and 3. The least common multiple of those would be 12. So the first thing I'm going to do is multiply both sides by positive 12. So that's going to keep the symbol the way it is. Right, so I'm gonna that side and this side 3/4 plus 8/3 times x. Right, multiplying both sides by positive 12. So the symbol didn't change. Right? And the right side has multiple terms, right? So I need to distribute the 12. And this should clear away all the denominators. Right, you have, 6 goes into 12 twice, 2 times -5, you have negative 10x on the left is, again, the symbol didn't change, is less than or equal. Now 12 times 3/4 is 9. And then 12 times 8/3 would be 32. So you have 32x there. Okay. Alright, and then all I would need to do here is subtract 32x from both sides. Now the symbol wouldn't flip, but on the left side I'd have negative 42x. Sorry, negative 10 minus 32. Negative 42x. On the right side I'd have just 9. Okay. And notice I didn't write the symbol yet because the next step, I don't want to write a whole nother line. The next step is going to be I'm going to divide both sides by negative 42. Divide by negative 42, and that will flip the symbol. So is greater than or equal to becomes is less is less than or equal to becomes is greater than or equal to. Right? And again, this flips the symbol here when you divide both sides by the same negative number, right, or multiply. Okay, so that's why the symbol got changed. Alright, so now I have x on the left is greater than or equal to, and then positive 9 divided by negative 42 would be negative. And they have a common factor of 3. This is 3 times 3, and this is 3 times 14. So x is greater than or equal to negative 3/14. Right. Negative 3/14. Just double checking. Yeah, absolutely. So here's what I'm going to use to write out all the stuff, right? So the solution set, right, a description of all the numbers that'll make this true. I'm going to do it in all 4 ways, right? This is, x can be replaced by any real number greater than or equal to negative 3/14. So all real numbers greater than or equal to, right? This is it's included this time. Negative 3/14. The graph, again the variable's x here, and I'll just put x next to the label. Got 0, now negative 3/14 is to the left of 0 here. And we're talking the numbers once again greater than this negative 3/14. So negative 2/14, negative 1/14, 0, 1, 2, 3. If you plug in 0, this should be true. You'd get 0 is less than 3/4, so less than or equal to 3/4. That's true. Plug in any number to the right of negative 3/14 to the original inequality, and it should be a true statement. But then we also have or equal to negative 3/14. Right? So again, a filled in dot, a closed solid dot above negative 3/14. It is included. And you can check that, right? Plug in negative 3/14 for x, and you'll see that this original inequality will be a true statement. Both sides will be equal in that case. The or equal to part will be satisfied. And then I leave it to you, if you want to plug in any number less than negative 3/14, say negative 4/14, negative 5/14, negative 1, negative 8, negative a million. This will be false. The left side will be greater than the right side, not less than or equal to. Then set builder notation, again, it's very simple once it's solved. It's all values of x such that x is greater than or equal to negative 3/14. And finally, the interval notation, right? The left end is at negative 3/14. The right end, well, there is no right end, so positive infinity. Always parentheses on the infinities. But this time, the left end, negative 3/14, is included. So I'm putting the rectangular bracket, right? Not a parenthesis. And that's what they want, right? The interval notation for the solution set. Excellent. Alright, so again, I'm doing the same thing every time here. Alright, so now instead of keep on rewriting the lines, I'm just going to write what I'm doing below it. So we have 4x minus 7 is less than or equal to 9. All I would do here is add 7 first to both sides, and that's just adding or subtracting. Alright, so the symbol would not flip. So we have 4x still is less than or equal to, and then 9 plus 7 is 16. Right, and then to get x alone, we divide both sides by 4. Right, I'll put division symbol divided by 4, divided by 4. Right, and that's a positive 4. Right, positive 4. So 4 this would be x on the left, and dividing by a positive number does not change the symbol. So it still is less than or equal to, and then 16 divided by 4 is positive 4. So there's we can describe the solutions here. All right, so all real numbers less than or x can be any number less than or equal to 4. Less than or equal to 4. The graph, again, the variable's x. I'll label the number line with that, and then here's 0. 4 would be to the right of 0 somewhere. But we're talking the numbers less than 4, right? To the left of 4, 3, 2, 1, 0, and so on. And 4 itself, right, should also be a solution. And you can check that. Plug in 4 for x, you'll get 9 is less than or equal to 9, right? That satisfies the equal to part. And then the set builder notation, it's the solutions are all values of x such that x is less than or equal to 4. Very simple. And then interval notation, right? There is no left end for this piece of solutions, right? This solution set. So that's negative infinity up to positive 4. Always parentheses on the infinities, and 4 is a solution. 4 is included, so I put a rectangular bracket on 4. And this is what they want, right? The interval notation for the solution set. But yeah, all 4 of these things, right? Every single time I've been doing the words, the graph, the set builder, the interval, they all describe the same set of numbers, right? So if you put either one of these, you'd be correct in stating the solutions. It's just they want interval notation. Alright, great. Alright, so next one, same deal. Again, I'm going to take all the variables to the left and non-variable terms to the right. So I'm going to subtract x from both sides. Then I'm going to subtract this 3 from the left and the right. And again, adding and subtracting doesn't change the symbol. Right? So on the left side we have negative 3x still is greater than. On the right side we have negative 8. Right? Negative 5 minus 3. And then I would divide by negative 3, right? So divided both sides by negative 3. And now the symbol will flip, right? And I'll write that here. Right? I know I didn't write it before, but I wrote it once before. but we're multiplying or dividing, and it's only, I'll say this every single time it happens, we're only going to flip the symbol when we multiply or divide both sides by a negative number, or if we switch sides, but that's why I want the variable on the left, so I don't want to switch sides. Dividing by -3, left side's x. Again, we divided both sides by a negative number, so the symbol will flip. Instead of is greater than, it'll be is less than. And then -8 divided by -3 would be positive 8/3, right, or positive 2 2/3. All right, so there you go. So this is, the solutions are, all real numbers less than 8/3, right? X is less than 8/3, but not including 8/3, right? So here's a graph. Once again, the variable's x, zeros here. This is positive 8/3, so that'd be somewhere to the right of 0. Our solutions are the numbers less than 8/3, right? So these numbers right to the left forever, but not 8/3 itself. So notice the big open hole point, open point above 8/3. And again, I leave it to you to test these values out back in the original inequality and see if you get true statements or not. Set builder notation, right? The solutions are all values of x such that x is less than 8/3, right? Very simple once you've solved. Right? And then finally, the interval notation for this same set, right? The solution interval here has no left end, so -infinity up into positive 8/3 on the right end, parentheses on both. Right? Neither one of those is included in the solution set. And that's what they wanted, right? The interval notation for the solution set. Okay, great. Doing the same thing every time here. Alright, now this one has some fractions. Once again, as I did with earlier problems, the least common denominator, the least common multiple of 2, 4, and 5 would be 20. Alright, so I'm going to multiply both sides. Let's put times 20 times 20. Alright, I'll dot 20. And just don't forget to do it to both terms on the right side there. Now this is positive 20 that I'm multiplying by, so the inequality symbol will not flip. Right, still going to be is less than or equal to. Left side would be negative 10x. Negative 5/4 times 20 would be negative 25. And then 2/5 times 20 would be 8. So I have negative 10x is less than or equal to negative 25 plus 8x. And then I'll subtract 8x from both sides. Now this is just subtraction, so the symbol does not flip. Right? Still is less than or equal to. Got negative 18x over here, negative 25 over here. Okay, and now I'm dividing by a negative number. This will flip the symbol. I'm going to divide both sides by negative 18. Right, divided by negative 18. And that will, flip the symbol. Because I'm multiplying or dividing both sides by a negative number. So we have x on the left. Now instead of less than or equal to, it is greater than or equal to. And then a negative divided by a negative is positive. Positive 25/18. And these don't have any common factor. So that's as simple as that gets. Now you could also write 1 7/18 if you want, but whatever. Right, this is it. The variables alone, I've solved the inequality. And if we want to describe the solutions, right, this is all real numbers. X can be any real number greater than or equal to 25/18. Greater than or equal to 25/18. The graph, again, these are x values here. Here's 0. 25/18 is positive, so it'd be somewhere to the right of 0. And we're talking the numbers greater than, right? So to the right of 25/18 or equal to. So solid point above 25/18, it is included, it is a solution. And again, I leave it to you to test some values out. Plug in 25/18 for x, plug in a number greater than 25/18 for x, and the initial inequality should be a true statement. Plug in a number less than 25/8, and the inequality should be false. Right? Set builder notation, right? It's all the solutions are all values of x such that x is greater than or equal to 25/18. And then finally, the interval notation, right? The left end is at 25/18. There is no right end, right? So infinity. 25/18 is a solution. Right? So I make a rectangular bracket around that, and always parentheses on the infinities. Great. All right, I just got one more page of these, doing the same thing every time. So just probably make these a little quick. All right, so for both of these, I would first get rid of the parentheses, simplify the sides, right? Distribute the -3 over here. We have -6x minus 3 is greater than, and then -2x minus 8, right? So I didn't do anything to any side. I just distributed the -3, distributed the -2 on their own respective sides. All right, so now comes the addition and subtraction part. I'm going to add 2x to get all the x's on the left, and then add 3 to get rid of that -3 and get all the constants on the right. And this is just addition or subtraction, right? So the symbol will not flip. And now I have -4x on the left and -5 on the right, -8 plus 3. And then to get the variable alone on the left side here, I'm going to divide by -4. Right, divided by -4. And that will flip the inequality. Okay, because you're multiplying or dividing both sides by the same negative number. So I have x on the left. Now instead of is greater than, it becomes is less than. And then -5 divided by -4, negative divided by negative would be positive 5/4, or 1.25, or 1 1/4, or whatever you want to write. So there's a description of the solutions, and I'll write it in all 4 ways, describe it in all 4 ways. So x can be any real number, or the solution set is all real numbers that are less than 5/4. The graph of this, values of x, here 0, that's positive 5/4 would be to the right of that. And it's just all the numbers less than 5/4 that are solutions here. So to the left of 5/4, but not 5/4 itself, right? So again, the open point above 5/4 telling me that is not a solution. And again, I leave it to you to test these values, see if the numbers I put that are solutions actually are, and the numbers that aren't solutions actually aren't. Right? Back in the original inequality, see if you get something that's true or false. Then the set builder notation, very simple, right? The solutions are all values of x such that x is less than 5/4. And then finally the interval for this picture, right, from -infinity to 5/4, right, left to right, and parentheses on both, right, because always on infinities, and 5/4 is not a solution, right? It's not included in the set. Great. So these can be very quick, right? And, if you know what you're doing, of course. Alright, so here the LCD is 15, right? You got 3, 5, and 5. The least common multiple is 15. So I'm going to multiply both sides by positive 15, right? This is dot 15 times 15. So the inequality won't change, right? We're multiplying both sides by positive 15. Right, now this first fraction on the left, 3 goes into 15 5 times. So you have 5 times, and then still this numerator, 5 times the quantity, x minus 1. Be careful with that. Right? 3 goes into 15 5 times. You got a factor of 5. And then that 5 is being multiplied by the entire numerator, right? The whole quantity, x minus 1. Same thing for this next fraction, right? Multiply that by 15. 5 goes into 15 3 times, so you have a factor of 3, and that's being multiplied by the entire numerator, the quantity x plus 2, right? Don't just write 3x plus 2, it's 3 times the quantity x plus 2. All right, then over here, 5 goes into 15 3 times, and 3 times 3 is 9, right? So you have just 9 on the right side. All right, so now I'm going to simplify the left side a bit. All right, we'll distribute the 5, distribute the 3, and combine like terms. So you have 5x plus 3x is 8x, and then negative 5 plus 6 would be positive 1. All right, 5 times negative 1 is negative 5, 3 times 2 is 6, negative 5 plus 6, positive 1. So the left side simplifies to 8x plus 1. The right side is still just 9. All right. Now I'll do some addition or subtraction to get the terms of the variable on the left side here. So I'd subtract 1 from both sides. Now that's just subtraction, so still the inequality symbol remains the same. Right? It still is less than or equal to. On the left side I have positive 8x. On the right side 9 minus 1 is positive 8. And then we're dividing both sides by 8. Right? And that will not change the symbol at all. Right? We're dividing by a positive 8. It's only when you multiply or divide by the same negative number that the inequality symbol will flip. All right, left side's x, right side's 1. There's your solutions described in an inequality. All right, the numbers that'll satisfy this inequality here are all the numbers that are less or equal to, less than or equal to 1. So all real numbers less than or equal to 1. Graph. Again, the variable's x. Here's 0. 1's to the right of 0. All the numbers less than 1 are to the left of 1 on the number line, right? So 0, negative 1, negative 2, negative 3, 1/2, whatever. All those are solutions. And so is 1 this time, right? Or equal to 1. 1 is included, so I put a solid point above it. And once again, I leave it to you to test these out. Plug in 1, plug in a number less than 1 for x back in the original inequality, and you'll see it's a true statement. And plug in a number greater than 1, 1.1, 2, 5, a million, and you'll see that this is a false statement. Those aren't solutions. The set builder notation, right? The solutions are all values of x such that x is less than or equal to 1. Very easy. And then finally, the interval for this piece here is, there is no left end, so negative infinity, comma, and then the right end is at 1. Always parentheses on the infinities, and 1 is a solution. So a rectangular bracket on that to indicate that it is included. Wonderful. All right, I'll circle that. Great. And that's it. All right, that was a lot, but I did the same thing every time. I just paid attention, made sure that when you added and subtracted something to both sides, the same thing to both sides. The inequality didn't change direction, didn't flip. When you multiplied or divided both sides by the same positive number, it didn't flip. It's when you multiply or divide both sides by the same negative number, like in example 8 here, right, that the inequality symbol changes direction, flips on you. That's really the only thing you need to pay attention to. Right? And also, I personally like having the variable on the left side, right? If it's on the right side, maybe just switch sides, make it easier to read. And don't forget too that if you do switch sides, the symbol will flip as well, but hopefully you're not having to switch sides too often. Great. And then you should be able to describe the solution set in words, in a graph, in this set builder notation, and also in interval notation. You should be able to describe a solution set in all 4 ways, and they all mean the same thing. All right, so I'm hoping that watching me go through these 9 examples here helps you out in some way when you're asked to solve a linear inequality in one variable on your own. and thank you very much for watching.